Hello and welcome back. This is the second part of a two-part lecture on foundational quantum algorithms. This part of the lecture is on the phase estimation problem and how we can solve it with a quantum computer. We'll also talk about how phase estimation can be applied to the integer factorization problem, and what we'll obtain is Shor's algorithm, which allows integers to be factorized efficiently on a quantum computer, which is something that we don't know how to do with a classical computer. We're going to start by briefly discussing eigenvectors and eigenvalues of matrices with a focus on unitary matrices. So let's suppose that M is an n by n matrix with complex number entries. Psi is a non-zero n-dimensional vector, again with complex number entries, and lambda is a complex number. Suppose further that M multiplied to psi is equal to lambda times psi. So for this particular vector psi, multiplying by the matrix M is equivalent to multiplying by the scalar lambda. It's then said that psi is an eigenvector of M and lambda is an eigenvalue of M, and more specifically, lambda is the eigenvalue that's associated with the eigenvector psi. This is a critically important concept in linear algebra, and we can often learn a great deal about matrices by thinking about their eigenvectors and eigenvalues. Now, there's quite a lot that can be said about eigenvectors and eigenvalues, but for the purposes of this presentation, I'm just going to mention a couple of basic facts concerning eigenvectors and eigenvalues of unitary matrices. First, every unitary matrix has an orthonormal basis of eigenvectors. That's not true for every n by n matrix, but it is true for unitary matrices, and in fact it's true for so-called normal matrices, which are matrices that commute with their own conjugate transposes, and that includes every unitary matrix. This more general fact is known as the spectral theorem, and it's a standard topic that's covered in linear algebra and matrix theory textbooks, in case you're interested in seeing how it's proved. The second fact that we need is that every eigenvalue of a unitary matrix lies on the complex unit circle. So one way to express these facts together in precise terms is shown here on the slide. For every n by n unitary matrix U, there's an orthonormal basis consisting of vectors psi 0 through psi n minus 1, along with real numbers theta 0 through theta n minus 1, such that multiplying each psi k by U is equivalent to multiplying each psi k by e to the 2 pi I times theta k. In general, for some arbitrary vector, this won't be how U works, but eigenvectors are special, and for every unitary matrix, we always have an orthonormal basis of these eigenvectors. Next, I'll define the phase estimation problem. For this problem, we're given two things. First, we're given the description of a unitary quantum circuit that acts on n qubits for some choice of n, and when we say that this is a unitary circuit, we just mean that all of the gates are unitary, so there aren't any measurements, and qubits aren't introduced or discarded in the circuit. Second, we're given an n-qubit quantum state vector psi. This part is a little bit unusual because we actually have a quantum state input for this problem, and it's a single copy of this state. It is more typical when we think about computational problems that the inputs are classical, either in the form of a string of bits or as a black box. But in this problem, we have a quantum state input. A natural way to think about this problem is that it's something that's likely to appear as a subproblem, and the phase estimation procedure that we'll eventually come up with is something that we generally use as a subroutine inside of some larger computation, such as one for a classical problem that we care about. Now, this is going to be a promise problem, and the state psi isn't just any old quantum state vector, but instead we're promised that psi is an eigenvector of whatever unitary operation U it is that the given circuit describes. And the goal is to find or to approximate the eigenvalue that corresponds to this eigenvector psi. Let's state the problem a little bit more precisely. The input consists of a unitary quantum circuit on n qubits, which can be encoded as a string of bits using whatever method you choose for quantum circuit descriptions, along with an n-qubit quantum state psi. We can call the circuit whatever we want, but what really matters in terms of the statement of this problem is the unitary operation itself that's performed when the circuit is run, and that unitary operation is described by the matrix U. But we're not given U as a matrix, we're just given the description of a quantum circuit that implements U. Notice, by the way, that there's no oracle or black box here. This is a genuine quantum circuit that could be described by a classical string of bits, so we're not working in the query model any longer. In essence, this quantum circuit will be playing a role that's similar to the oracle in Deutsch's algorithm, but it's given as a quantum circuit rather than as a query gate. The promise, as I've already stated, is that psi is an eigenvector of u, so if we ran our circuit on psi, we'd get psi coming out multiplied by whatever the eigenvalue is, and that would be a global phase in this situation. And finally, the output of the problem is an approximation to the eigenvalue corresponding to psi. And specifically, we're looking for an approximation to the real number theta between 0 and 1, including 0, but not including 1, that satisfies the equation that's shown on the slide. To explain this way of parameterizing the eigenvalue corresponding to psi, and also to clarify what we mean by an approximation, let's draw a picture of the complex unit circle. So here we can see the numbers 1, I, -1, and -I in their usual places, and we can consider some arbitrary point on the unit circle parameterized by theta as we have in the problem statement. This is the point we get if we start at 1 and we rotate by an angle of 2 times pi times theta. So the angle is at theta, it's 2 pi theta. And another way of thinking about that is that if we start at 1 and we travel a distance of 2 pi times theta on the unit circle itself, then we will get to our point. Every point on the inner circle can be represented in this way for a unique choice of theta, and that's because we go all the way around the circle as theta goes from 0 to 1, and if we went all the way to theta equals 1, we'd be back where we started at theta equals 0, so that's why we include 0 but not 1. Just to be sure that each point on the unit circle corresponds to a unique value of theta in the range that we're considering. There are various ways that we could imagine approximating a particular value of theta, but the way that we'll do it is to approximate theta with a fraction of the form that's shown here, where the denominator is 2 to the power m for some choice of a positive integer m, and the numerator is an integer y between 0 and 2 to the m minus 1. And to be clear, when we think about approximations in this context, it should be understood that values of theta near 0 and values of theta near 1 are in fact close together. For example, if theta is equal to 0.99, and we approximate this value of theta by the value 0, then it's actually a pretty good approximation in the sense that it's within 1 over 100 of the actual value if we wrap around and go back to 0 when we get to 1. The term modulo 1 is sometimes used to describe this situation where we're essentially equating theta equals 1 with theta equals 0, or in other words, we're throwing away the integer part of a number and just keeping the fractional part. The point is that what we really care about is the location of the point e to the 2 pi I theta on the unit circle, and thinking about this way of approximating theta makes sense when we have that aim in mind. The problem statement itself, as it appears here, isn't specific about how good the approximation to theta needs to be. That's something that we can fine-tune depending upon our needs. In some situations, we might be satisfied with a low precision approximation to theta, and in other situations, we might demand a high precision approximation, and the problem statement can be refined accordingly. Next, we'll see how we can solve the phase estimation problem with the quantum computer, and we'll start with a warm-up. This won't be our final solution to the problem. What we'll do is we'll make use of the phase kickback phenomenon to try to learn something about the eigenvalue for a given eigenvector. So we're given a description of a unitary quantum circuit for some operation u, and what we do first is to use this circuit description to create a new circuit that implements a controlled u operation, like is pictured on the slide. This is a pretty simple thing to do. What we can do is we can add a control qubit, which is pictured on the top in this diagram, and then use this control qubit as a control for every single gate that appears in the circuit for u. So all of the gates are applied if this control qubit is set to 1, and none of them are applied if the control qubit is set to 0. That means that we're going to need a controlled version of every gate that appears in the circuit for u, but these new controlled gates don't literally need to be single gates. They could be implemented as small circuits made out of gates from some universal gate set. And once we have a controlled version of u, we can consider running the circuit that's shown here, where we first put the control qubit into a superposition of 0 and 1, and then apply the controlled u gate to the eigenvector psi that we're given, and then we apply a Hadamard gate to the control and measure. We'll see why it makes sense to do this as we go through the analysis, but even before we get into the details, we can immediately see a similarity with Deutsch's algorithm, where we're applying a couple of Hadamard gates and measuring as a way of effectively probing what it is that some given operation is doing. Here, it's a controlled unitary rather than a query gate, but there are very similar ideas at play. So let's see what the circuit actually does. The initial state is the eigenvector psi tensored with the 0 state for the control qubit. Applying the first Hadamard gate transforms the state of the top qubit to a plus state, and we can expand the entire state as is shown right here. We can then apply the controlled U operation, and what that does is to apply U to psi when the control is set to 1, but not when it's set to 0. And so we get the state pi2 that's written on the screen. We can simplify the state using the fact that psi is an eigenvector of U with eigenvalue e to the 2 pi I theta. So we get that the eigenvalue is multiplying the second term, but not the first. And we can simplify using the bilinearity of the tensor product. So what we have here is the phase kickback phenomenon, but this time it's happening for some arbitrary eigenvector psi of an arbitrary unitary operation U, as opposed to a not operation being applied to a minus state more specifically. So that's the state after the controlled U operation is applied. By the way, it's worth taking a moment here to notice that the state of the bottom n qubits is still the eigenvector psi, and that's good because this gives us an opportunity to use that state again if we choose to do that. So then the second Hadamard gate is performed, and this is the state that we get. I haven't shown the computation here, but if you apply the Hadamard gate and simplify, this is what you should get. So that's the state just prior to the measurement. And now we'll focus in on this state to see what we learn about theta by measuring. If we measure the top or the rightmost qubit, these are the probabilities we get for the two outcomes. And here to get these probabilities, I've used a couple of basic formulas that relate sines and cosines to complex exponentials, just to express them in terms of sines and cosines. Specifically, the probability to get 0 is the cosine squared of pi times theta, and the probability to get 1 is the sine squared of the same angle. And this makes sense because the sine squared plus the cosine squared of any angle is 1, so our probabilities sum to 1 as we expect them. Here's a plot of these probabilities as a function of theta. And just to be clear about this diagram, this is a plot of the probabilities themselves, as opposed to being a plot that's depicting a single probability distribution, for instance. So for example, if theta is equal to a half, then the probability that we get the outcome 1, which is drawn in purple, is equal to 1, while the probability to get the outcome 0, which is drawn in blue, is 0. On the other hand, if theta equals 1/4 or 3/4, for instance, then we see that each of the two outcomes is equally likely. So we don't learn exactly what theta is from this procedure, but it does give us some information about theta. And if we imagine a situation in which we're promised that theta is equal to 0 or theta equals 1/2, for instance, then this procedure will tell us which one it is without any error. So that's a simple way that we can use the phase kickback phenomenon to learn something about the eigenvalue. But how can we learn more about theta? Well, this is the kind of situation in which I like to say that ignorance can be a guide, because there really aren't too many things that we can do. We don't know much of anything about the eigenvector psi, and we don't know that much about the operation U. We have a circuit for U, but for all we know, it's a confusing mess that we wouldn't be able to make any sense of if we were to try to examine it. But one very simple and natural option is to run the circuit multiple times. In particular, we could try to do exactly the same thing that we just did, except that instead of applying a single controlled U operation, we can apply that operation twice. Or we could apply it any number of times, but let's start with twice to see what happens. Well, it's actually pretty simple what happens. By applying the controlled U operation twice, we're effectively just squaring the eigenvalue, because it'll get kicked into the phase of the top qubit 2 times rather than just once. And so, when we think about the outcome probabilities as a function of theta, we're essentially just doubling the frequency. For each possible choice of theta, the outcome probabilities are the same as they would be if we doubled theta and then took the fractional part to get a number between 0 and 1. For example, if theta is a half, then the eigenvalue is -1, and by applying u twice, we're effectively squaring the eigenvalue, and we see that the result is the same as if theta is equal to 0, which is that the probability for the outcome 0, which is pictured in blue, is equal to 1, and the probability for the outcome 1, which is pictured in purple, is equal to 0. This is very simple, but we can in fact get some additional information about theta by doing this. For example, if we knew in advance that either theta is 0 or theta is a quarter, then this circuit will reveal to us which of the two possibilities it is. But on the other hand, we can no longer distinguish the case that theta is 0 from the case that theta equals 1/2. So this procedure isn't strictly better than the one from before, where we had just a single controlled U gate, but by also running the circuit, we can get some additional information. It's not immediately clear how the additional information that we can get by iterating the controlled U operation multiple times can be reconciled with the information that we get by performing it just once. And in fact, there are multiple ways to proceed. I'm going to describe what could be called the traditional approach, where we use a single quantum circuit that has multiple control qubits that control different numbers of iterations of the unitary operation U. First, I'll describe how this works for 2 control qubits, and then a bit later we'll generalize it to more than 2 control qubits. Here's a quantum circuit that uses 2 control qubits. The top control qubit controls a single U operation, while the second from top qubit controls 2 copies of U. So what we're doing is combining the 2 circuits that we saw previously in a way that makes use of the single copy of the eigenvector psi that we have. You'll notice, however, that the Hadamard gates after the controlled U operations have been removed, and there are no longer any measurements. So what we're going to do is we're going to see how this circuit works, and then we'll figure out what we should do with the top 2 qubits in order to learn as much as we possibly can about the value theta that we're trying to estimate. After the Hadamard gates are performed, we have the state that's shown here, and this is going to be a convenient way of writing this state to see what happens next. A0 and A1 are bits, and if we think about the top 2 qubits as being a 2-qubit register, then we're thinking about A0, which corresponds to the top qubit, as being the lesser significant bit, and A1, which corresponds to the lower control qubit, as being the more significant bit. After the first control U operation is performed, we'll obtain the state that's shown here. The classical state corresponding to the top control qubit is A0, so the result of the phase kickback can be expressed in this way. Then, after the second and third controlled U operations are performed, we'll obtain this state. The idea is the same as the first one, except this time we're applying the controlled U operation twice, so we multiply A1 by 2 in the exponent to reflect that. And now we can simplify this expression by thinking about the bits A1 and A0 together as an integer between 0 and 3 using binary notation. That is, when we think about the 2-bit string A1, A0 as the binary encoding of an integer, what we get is 2 times A1 plus A0. And the understanding is that when we write ket x, we're talking about x written as a binary string of length 2 using binary notation. So now let's focus in on these 2 control qubits to try to figure out what we can learn about theta from them when they're in this state. The remaining n qubits are still in the same state psi that we were originally given, and that really is a great thing about this approach because, like I said, we can use that state again if we want to try to gain even more information about theta. But for now, let's just think about what we can learn from the 2 control qubits. To help us to figure this out, let's imagine that we're promised that theta is equal to y over 4 for some integer y between 0 and 3. In general, theta might not be one of those 4 values, but this is a natural case to consider. We saw in the original single control qubit version of the procedure that if we were promised that theta is either 0 or 1/2, the circuit would reveal which one it was. And we also noticed that in the version where we applied the controlled U operation twice, we could effectively discriminate the case theta equals 0 from the case that theta equals 1/4. So we might hope that with our new circuit, we can discriminate these 4 cases. In essence, what we're doing is we're using the notion of a promise problem just to try to make the problem easier for us so that we can see how to proceed. Let's define a 2-qubit state for each of the possibilities. Specifically, phi y is equal to the states that's shown on the top of the slide when theta is chosen to be y/4 for each of the 4 choices of y, and here are those 4 states written out explicitly. So just to reiterate, if theta is equal to y/4 for y being 0, 1, 2, or 3, and we run our circuit, we're going to be left with one of these 4 states, whichever one corresponds to the correct value of y, and we just want to try to figure out which one it is. And the question is it possible? Can we figure out which one it is? And the answer to that question is yes, because these 4 states are orthonormal. They're all unit vectors, of course, because they're quantum states, and if you compute the inner product between any pair of them, you will get 0, and I'll leave that for you to check on your own. Because they're orthonormal, that means that they can be perfectly discriminated by a projective measurement. And in particular, we can express such a measurement by defining one projection for each vector like we have here. This always works anytime we have an orthonormal basis, and we conclude that it is therefore possible to accomplish our task, which is to learn the value of y from the state shown at the top of the screen. And if we'd like to do that with a quantum circuit, we can proceed as I will now explain. First, we can define a unitary matrix V whose columns are the 4 vectors listed in order. That matrix will have the action that's described on the bottom of the slide on the 4 standard basis states, and we can easily write down the matrix like this to see what it looks like. Because V maps each standard basis state ket y to the vector phi y, we see that by applying V dagger, or in other words V inverse, to phi y, we'll transform it back the other way so that we'll get the corresponding standard basis state. So what we can do is to simply apply V dagger to whatever state we obtain from our circuit, and then if we perform a standard basis measurement, we'll see the number y we're looking for expressed as a string of length 2 written in binary. Before we go any further, let's talk a little bit more about the unitary matrix V. This is a very special matrix, and you may have seen it before. It's the matrix that's associated with a linear operation on 4-dimensional vectors known as the discrete Fourier transform. To be more precise, the discrete Fourier transform can be defined for any positive integer dimension, and we'll see what it looks like in general in just a few moments, and this is what it looks like specifically when the dimension is 4. We can think about the discrete Fourier transform in different ways. We can think about it purely abstractly as a linear mapping on vectors that can be represented by a matrix. And we can also think about it as a computational problem where we're given a vector and we want to compute the result of applying this linear mapping. That turns out to be an incredibly important computational problem. And there's a highly efficient algorithm for performing that computation known as the fast Fourier transform, which changed the world. We can also think about the discrete Fourier transform as a unitary quantum operation that can be applied to a quantum state vector. And when we think about it in this way, we call it the quantum Fourier transform, or the QFT for short. Mathematically speaking, it's essentially the same thing as the discrete Fourier transform, but we call it the quantum Fourier transform just to clarify that it's an operation being applied to a quantum state vector. So let's change the name of our matrix from V to QFT4 to reflect the fact that the operation that we've come up with is the quantum Fourier transform. So here's the complete circuit for learning the value of y when we're promised that theta is equal to y/4 for y being 0, 1, 2, or 3. And just to make sure that it's clear, we're applying the inverse of the quantum Fourier transform, or in other words, QFT4 dagger, to map one of our 4 possible states back to the standard basis state ket y, so that we can recover y by measuring in the standard basis. So that's the circuit that we get from thinking about a promised version of the phase estimation problem, where we're promised that theta is 0, 1/4, 1/2, or 3/4, but there's nothing that prevents us from running this circuit for an arbitrary value of theta. And if we do that, here are the probabilities of the 4 possible outcomes that we obtain. Each of the 4 possible values for y has its own color, and the plot tells us what the probabilities are for each one as a function of theta. So for instance, if theta is 3/4, we'll get the outcome 3 with probability 1, while the probabilities of the other 3 outcomes are 0. If theta is close to 3/4, but it's not exactly 3/4, then there will be some non-zero probability associated with the other outcomes, but we'll still get the outcome 3 with high probability. So even though theta may not be equal to y/4, we can still think about the outcome that we get from the measurements divided by 4 as being a guess or an approximation for theta. The guess might be wrong, but nevertheless it is providing us with information. And one thing that we can see from the plot is that best approximations always have the highest probabilities associated with them. And when I say best approximation, I mean whatever value of y/4 is closest to the true value of theta in the modulo 1 sense. The worst possible case is that theta is exactly halfway between two values of y/4. For example, if theta is 3/8 or 0.375. In this case, we see that the approximations 1/4 and 2/4 are equally good. So in this particular case, there are actually two best approximations rather than one, and we're equally likely to get these two best approximations. The other outcomes, 0 and 3, which don't give good approximations to theta when we divide by 4, actually do appear with some probability, which looks like it's just under 10% in both cases. So this procedure isn't perfect, but it does provide us with information, and it's quite noteworthy that regardless of theta, we're always guaranteed to draw either the best approximation or one of the two best approximations when there's a tie, with probability that appears to be just above 40%. And the closer theta is to the approximation, the higher the probability to see the corresponding value of y. And that's a pretty significant improvement over using a single control qubit. This is, in fact, the phase estimation procedure when we choose to use two control qubits. And what we'll do next is that we will generalize the procedure where we don't stop with just two control qubits, but we use however many control qubits we choose to use. And what we'll see is that by generalizing this procedure, by adding more control qubits, we'll be able to get more and more accurate approximations of theta. And the end result will be the general phase estimation procedure. In order to generalize the phase estimation procedure from two control qubits to however many we choose, we're going to need to understand how the quantum Fourier transform is defined for other dimensions. And we're also going to need to discuss how it can be implemented with a quantum circuit. Here's the definition of the quantum Fourier transform when the dimension is an arbitrary positive integer n. We're thinking about this operation as being an operation on a system whose classical states are 0 up to n-1. And here, the matrix that describes this operation has been expressed using Dirac notation. We can also describe it in terms of its action on standard basis states, like is shown here, just to connect it to what we just saw when n is equal to 4. So here's what it looks like when n is equal to 1, which isn't a very interesting case. Here it is for n equals 2, and you'll notice that what we get in this case is a Hadamard operation. Here's the quantum Fourier transform for n equals 3, for n equals 4, which we've already seen, and for one last example, here it is for n equals 8. Here's some notation that's going to be useful going forward. Define a complex number omega n like is shown here. Specifically, omega n is e to the 2 pi I over n, which can also be written in terms of sines and cosines, like is shown on the slide. And here's a figure that shows a few examples. Omega 1 is equal to 1, omega 2 is equal to -1, omega 4 is equal to I, and in general, to get omega n, we can imagine slicing the unit circle into n equal size pieces, and omega n is at the corner of the first piece, assuming that the other corner of that piece is 1. So in particular, as n gets larger and larger, omega n will get closer and closer to 1. And now, if we use that notation, we can express the quantum Fourier transform in a slightly cleaner way like this. There's an efficient quantum circuit implementation of the quantum Fourier transform when n is a power of 2, which we'll now take a look at. Although we can define the quantum Fourier transform for any dimension n, we're only going to need it in the case that n is a power of 2 for phase estimation. The implementation will make use of controlled phase gates, which are depicted as is shown on the slide. They look like two controls connected together, along with a number, which is alpha in this case. And the action of this gate is described by the matrix that's also shown. These are literally controlled phase gates, meaning that we have a control qubit that controls a phase gate. But for phase gates specifically, it doesn't actually matter which of the qubits is the control and which is the target. And now that we have that notation, we can see how the quantum Fourier transform can be implemented. The implementation is recursive in nature, and perhaps the easiest way to describe it in simple terms is to give an example that can be easily generalized. So here's how we can do it when n is equal to 32. So there are 5 qubits in this case. The first thing that we do is to apply the quantum Fourier transform to all of the qubits except for the least significant qubit, which is the top one, and that's the recursive part. So to implement this operation, we have to follow the same pattern, but for one fewer qubit. And in the base case, we have just a single qubit, for which the quantum Fourier transform is just a Hadamard gate. Once we apply the QFT on all of the qubits except for the top one, we apply a bunch of controlled phase gates using the phases that are indicated in the diagram. We then apply a Hadamard gate to the top qubit and then shuffle the qubits around using some swap gates. The swap gates have the effect of cyclically permuting the qubits, which is just something that's needed to make the construction work. We can follow exactly the same pattern for other choices of n, provided that the powers of 2, where we always start the controlled phase gates with alpha being pi over 2 for the bottom qubit, dividing by 2 each time to get the subsequent phases. The controlled phase gates, by the way, all commute with one another, so it doesn't actually matter in what order they're applied. Now, it is absolutely not at all obvious that this construction works, and I'm not going to explain why it works in this presentation, but what I will say is that what's being exploited here is the basic structure of the discrete Fourier transform, and in fact, it's exactly the same structure that allows the fast Fourier transform to work the way it does. So how many gates do we need in total for this implementation? Well, to figure it out, let's let Sm be the number of gates we need when we have m qubits. When m is equal to 1, we need just a single gate because the QFT is just a Hadamard operation in this case. If m is at least 2, then these are the gates that we need. We need Sm-1 gates for the quantum Fourier transform on m-1 qubits, whatever that number happens to be. We need m-1 controlled phase gates, m-1 swap gates, and 1 additional Hadamard gate. So here's an expression of Sm in both cases when m is equal to 1 and when m is at least 2. This is an example of what's called a recurrence relation, and they show up very commonly in the analysis of algorithms. This particular one happens to be very simple, and it has a so-called closed form expression, which we can obtain by summing. To be precise, the value Sm is the sum of the first m consecutive odd integers, which equals m squared, as you may have either encountered before, or maybe you simply noticed it at some point in your life. And it's pretty easy to prove that this formula is true by induction on m. So that's it. We can implement the quantum Fourier transform on m qubits using m squared gates. Just a couple of very quick additional remarks. First, we don't actually need all of the swap gates that I've described. It is possible to push them all out to the end, so to speak, so long as we adjust which qubits the controlled phase gates act upon. And if we do that, we actually only need m over 2 swap gates in total, rounding down in case m is odd. We'll still have a quadratic cost, but the number of gates can be reduced by doing this nevertheless. And one additional remark is that we can actually make the cost even less than that. And that's particularly simple if we're willing to settle for a good approximation. For example, when m gets large, a lot of the controlled phase gates are actually very, very close to the identity operation. And by eliminating the ones that are very close to the identity, we can save a lot of gates while still getting a pretty good approximation. It's also possible to approximate the quantum Fourier transform with very shallow circuits, meaning ones with small depth, in case that's something that we wish to do. And now that we know what the quantum Fourier transform is for different dimensions, as well as how we can implement it when the dimension is power of 2, we can go back to the phase estimation procedure and see how it can be generalized, where we use some arbitrary number m of control qubits. Here's what the procedure looks like as a quantum circuit for an arbitrary choice of m. We have m control qubits on top, which we assume are all initialized to the 0 state. We apply a Hadamard gate to each one of them, and then each one of them is used as a control qubit to apply some power of the operation u, where we double the number of times u is applied for each control qubit. Here in this diagram, I've indicated this by including the powers on u inside of the boxes rather than showing the controlled u gate being applied that many times, just as a way of making the diagram more clear and also saving space. Now, the first thing that we need to notice about this procedure is that it might become very expensive. In particular, we're doubling the number of times each u operation gets applied for each control qubit. And if the way that we do this is simply to iterate a controlled u gate however many times we need, we're going to get a huge circuit. It's going to be exponentially large in the number m. That is a major limitation in general, and in particular, it limits our ability to get precise approximations of eigenvalues. In the specific case of factoring, which we'll get to shortly, it turns out that we're very fortunate and we can play a trick that allows us to avoid this exponential blowup in cost. But in general, for an arbitrary unitary operation u, this will not be possible, and we'll pay a steep price for increasing the number of control qubits. I'm not going to go through a detailed analysis of this circuit in this presentation, and instead I'll just mention that there is a fairly simple expression for the state just prior to the measurements, which is shown on the bottom of the slide, and it's a good exercise to verify that if you're so inclined. From that state, we get an expression for the probabilities of the various outcomes, and it happens to look like this. And once we have this expression, we can reason about it, and really this expression is all that we need to carry on. In essence, what we find is that the situation is not all that different from the m equals 2 case, except that we'll get more precision. In particular, we can think first about the probability to get the very best, or one of the two best approximations, which we can express as is shown here. You can ignore the subscript of 1 on the absolute value if you like. This is just a symbol that we can use to remind ourselves that we're talking about approximations on the circle where we're thinking about theta equals 0 and theta equals 1 as being the same. But anyway, the point here is that we're thinking about whatever choice of y makes y over 2 to the m as close as possible to theta. And once again, just like we had for the m equals 2 case, we're guaranteed to get this outcome y with probability at least 40%. In fact, the lower bound isn't 40%, it's 4 over pi squared, which is just above 40%. And that's actually pretty remarkable. What we're talking about here is getting the very best approximation to theta as a fraction y over 2 to the m, where m is an integer, and we're getting this best approximation with better than a 40% chance. We can also think about approximations that are worse, and specifically, let's imagine that y isn't quite so good, and more specifically, let's suppose that there's a better approximation to theta of the same form that lies between theta and y over 2 to the n, which can be expressed as is written here on the slide. In such a case, the probability to get this y will be relatively small. It'll be at most 25%. It'll actually be lower than that. 25% is what we get from a pretty casual analysis, but it's good enough for our needs. As an example, here is the plot that we get when we use 3 control qubits rather than 2. This time I'm only plotting the probabilities for the outcomes 3, 4, and 5, because I don't want the figure to become too messy. And as you can see, when theta equals 1/2, for instance, we're guaranteed to get to the outcome 4. And so we take our approximation to be 4 over 8, and we're exactly right. As long as theta is closer to 1/2 than it is to 3/8, for instance, we'll get the outcome 4 with a probability larger than the outcome 3, and with probability larger than 40%. Here's the plot when m is equal to 4. And the curves actually look pretty much identical, except that now we've zoomed in by a factor of 2. So now the outcomes that are plotted include 7, 8, and 9, and we're taking the approximation to be one of these numbers divided by 16 rather than 8. And I'll show one more plot where we increase m to 5, and again, we're going to be zooming in by a factor of 2. And here it is. The curves look pretty much identical again, but we're effectively doubling our precision. And once again, we have the very best approximation to theta appearing with probability greater than 40%. So that's pretty amazing. And if 40% is not good enough as a measure of confidence, what we can do is we can run the procedure a small number of times and take the outcome that appears most frequently. And if we do that, we'll be extremely likely to end up with a very good approximation to theta. And remember, by the way, that every time we run the phase estimation procedure, we have that the eigenvector comes out unchanged. So it is available for us to run the procedure multiple times like this. In short, what we're doing is we're gathering statistics about theta. And the point is that by doing this, we can get a very precise estimate for theta with very high confidence, and we don't need all that many iterations of the procedure to do this. And that is how the phase estimation procedure works. In the last part of the lecture, we'll apply the technique of phase estimation to the integer factorization problem. The way this works is that we consider an intermediate problem known as the order finding problem. Here's a statement of the order finding problem. The input consists of two positive integers, a and n, which are assumed to have greatest common divisor equal to 1. And the output is the smallest positive integer r, such that a to the power r is congruent to 1 modulo n, or equivalently, the smallest positive integer r for which a to the power r divided by n has remainder equal to 1. There will, by the way, always be such a positive integer r, and this number is called the order of a modulo n. Now, this is believed to be a computationally difficult problem in the sense that no efficient classical algorithm is known to solve it. And the reason it's relevant to us is that it's at least as hard as integer factorization, in the sense that if we have an efficient algorithm for order finding, then we can use it to solve the integer factorization problem efficiently. In particular, we can use the following probabilistic method to attempt to find a non-trivial factor of a given positive integer n, given the ability to solve the order finding problem. And by the way, this method only works when n is an odd number and when it is not a prime number raised to a power. Those two cases, when n is even or a prime power, can be handled separately. It's trivial, of course, to identify 2 as a factor of any even number, and prime powers can be factored efficiently by a classical algorithm. So for this method, n is an odd number and it is not a prime power, which is to say that there are at least 2 different prime numbers that divide n. First, we choose a between 2 and n-1 at random uniformly. We then compute the greatest common divisor of a and n. And if the GCD happens to be larger than 1, then we've just been incredibly lucky, and the GCD will be a factor of n, so we can just output it and stop. Otherwise, the algorithm continues on, and the next step is to compute the order of a modulo n, which is where we need a quantum computer. Or maybe we have a different method to compute the order. The algorithm doesn't care where it comes from, but the only way that we know how to do this efficiently in general is with a quantum computer. If the order r is even, then we compute the GCD of a to the power r over 2 minus 1 with n. And if that GCD is larger than 1, then again we have a factor of n, so we output it and stop. Otherwise, the algorithm has failed, and in that case, we can go back to the start, choose a different a, and hope for a better outcome the next time around. And that's it. And by the way, once we've found a factor of n, we can then recurse on both that number and n divided by that number until we have a prime factorization to bed. Like I said, this is a probabilistic method, and it can be proved with a little bit of basic number theory that it succeeds with probability at least 1/2. If it doesn't succeed, we can simply try again with a different choice of a, or we can decide to give up, but it's not likely that we'll need to run it too many times to succeed. So why should this work? Here's the main idea. First, because a to the power r is congruent to 1 modulo n, we have that n divides a to the power r minus 1, and in fact those two statements are equivalent. If r is even, then the equation shown here is true. This is the well-known formula for the difference of squares. The equation is actually true for all r, but we need r over 2 to be an integer for this all to work out. And so if we put these two facts together, we see that every prime factor of n must divide one of the two expressions in parentheses, because that's the only way that n can divide the product. Now, it could be that every single prime factor of n divides the first expression in parentheses and not the second, but for a random choice of a, that's not very likely to happen given our assumptions on n. And so when we compute the GCD in step 4, we're likely to get the product of some of the prime factors of n, but not all of them. To analyze this carefully requires some number theory, like I said, but it is pretty basic number theory. So the upshot is that if we have an efficient algorithm for solving the order finding problem, then we can use it to factor integers efficiently with high probability. The last thing that we need to do is to figure out how to solve the order finding problem on a quantum computer using phase estimation. So let's assume capital N is a positive integer, and let's let small n denote the number of bits that we need to express n-1 in binary notation, which means that any number between 0 and n-1 can be expressed in binary using little n bits. Next, for any integer a whose GCD with n is equal to 1, define an operation ma like is shown here. In words, what ma does to numbers between 0 and n-1 is to multiply by a and take the remainder modulo n, and for numbers equal to or larger than n, the operation doesn't do anything. This is a unitary operation, but that's only true because the GCD of a and n is equal to 1. If the GCD isn't 1, this operation won't be unitary, but we don't care about that. The order isn't defined in that case either. We're only going to care about this operation when the GCD is equal to 1. I won't explain how it's done in this presentation, but it is possible to build quantum circuits that perform these operations using big O of little n squared gates. That's not obvious, but it is true, and it follows from the fact that we can perform these operations classically using big O of n squared bit operations. And here's the main idea. The eigenvalues of MA are very closely connected with the order of A. And by using phase estimation to approximate these eigenvalues closely enough, we'll be able to determine the order of A. So what exactly are the eigenvectors and eigenvalues of MA? Well, we're not going to need to know all of them. We only need some of them. And to describe the ones that we need, I'm going to use the following notation. First, we'll continue to let R denote the order of A modulo n. So R is what we're actually trying to find. And second, just to avoid clutter, let's assume hereafter that every expression inside of a ket is implicitly taken modulo n, so we don't have to keep on writing mod n over and over. I'm also going to refer to omega r, which is e to the power 2 pi I divided by r. So that's the same notation as before when we talked about the quantum Fourier transform, except we're using r, the order, instead of the number n. So let's start off with an easy example. Here's an eigenvector of MA. We've named it psi 0, and it's given by the sum of ket 1, ket A squared, ket A cubed, and so on, up to ket A to the power r minus 1, everything modulo n, and all divided by the square root of r to make it a unit vector. The eigenvalue associated with this eigenvector is 1, which means that theta equals 0 in the context of phase estimation. And we can verify this by applying MA to the vector psi 0. MA multiplies by A modulo n, so each exponent gets increased by 1, and because A to the power r equals 1, we see that it basically wraps around and we get the original vector back. That's a very simple example of an eigenvector, but it doesn't turn out to be all that useful, because if we have this eigenvector and we perform phase estimation, all we're going to get is an approximation to the number 0, and that doesn't tell us anything about the order. So let's look at some other eigenvectors. Here's one named psi 1. It's similar to psi 0. We have exactly the same kets, and we're summing them up and dividing by the square root of r. But this time we have various phases multiplying each of the kets. Omega r to the -1 for a, omega r to the -2 for a squared, and so on, up to omega r to the power -r-1 for a to the power r-1. So the power of omega r is always -1 times whatever power of a appears in the ket. And this time the eigenvalue is omega r. And you can check that by multiplying the vector by ma, which increases the exponents just like before. This time, however, we do have to pull out a factor of omega r to get the original vector psi1 back. So that factor of omega r represents the eigenvalue that's associated with the eigenvector. And for this one, it is evident that the eigenvalue does tell us something about the order. In particular, if we perform phase estimation, we'll get an approximation to theta, and if we have enough precision, we can then learn r simply by taking the reciprocal and rounding to the nearest integer. Keep in mind, though, that we only have an approximation to theta, and we can't afford to confuse r with r+1 or r-1, for instance. And what that means is that we do, in fact, need a fair bit of precision to correctly recover r. So that's the second eigenvector-eigenvalue pair of ma, and we can identify additional eigenvectors using exactly the same reasoning. And in fact, if we simply replace omega r with omega r to the power j for each j between 0 and r-1, we'll always get an eigenvector, and the associated eigenvalue will be omega r to the power j. So this actually includes psi0 and psi1, which we've already seen, as well as r-2 other eigenvector-eigenvalue pairs. They all work in basically the same way, and to verify them, we just need to know that a to the power r equals 1, as well as omega r to the power r equals 1. There are additional eigenvectors of ma, but they aren't going to be useful to us, and we don't need to worry about them. We only need to worry about psi0 through psi r-1. Unfortunately, it's not so easy to get our hands on any of these eigenvectors directly, so what we do instead is to use the state ket1 rather than an eigenvector, meaning the standard basis state that encodes 1 in binary. The idea is that this is essentially going to give us psi j for a random j, and here's the equation that's the key to why this works. Ket1 is a uniform superposition of psi0 through psi r-1. The end result, as I suggested a moment ago, is that using this vector in place of an eigenvector will cause the phase estimation procedure to output an approximation to j over r for a random choice of j. I am skipping a lot of details here, by the way. The point here isn't to explain this in its entirety, but rather to just give you the basic idea for how it works. Anyway, if we do this with enough precision and we repeat a small number of times, then we will be very likely to have gained enough information that we can recover the order r. The specific way that this works involves an efficient classical algorithm that's known as the continued fraction algorithm, but I am going to skip the details of that for the sake of this presentation. It remains to consider the implementation, and in particular to figure out how much it costs. Here's the phase estimation procedure applied to the operation ma, where we're using ket1 in place of an eigenvector. And although I kind of glossed over it on the previous slide, if we want enough precision to make it all work, it suffices to take the number m, which is the number of control qubits on the top of the circuit, to be 2 times little n, so we have 3 times little n qubits in total here. So let's figure out what the cost of doing this is as a function of little n, which is the number of bits that we need to write any interesting choice of capital N, the number that we're trying to factor in binary notation. First, let's think about the controlled unitary gates. As I mentioned earlier in the lecture, we can implement MA using big O of little n squared gates based on efficient classical algorithms for arithmetic modulo n. It's not enough, though, to implement just MA. We also need to implement MA squared, MA to the 4th power, to the 8th power, and so on, all the way up to MA to a power that's exponential in M, and we need to take M to be linear in little n to get enough precision. So that's a big concern. And if we were to implement powers of MA by simply iterating MA, we'd be in big trouble because all of these iterations of MA would require an exponential number of gates. But fortunately, we can play a trick to avoid this exponential blowup in cost. What we can do for each power k that we need is to first compute a to the power k modulo n with a classical computer, and let's call that number b. And then we'll simply use the circuit for MB in place of k iterations of the circuit for MA. And that's it. B is just some number between 1 and n minus 1 that has GCD equal to 1 with n. So we only need big O of little n squared gates to implement MB. Basically, in a nutshell, what we're doing is we're exponentiating with a classical computation rather than iterating a quantum circuit. But the actual operation that we get is the same either way. It's just multiplication by a k times. This is actually kind of a miracle, in fact, and we wouldn't be able to solve the order finding problem or factor integer sufficiently with a quantum computer if it wasn't for this. The whole approach would simply be too expensive. And now that we know that each of the controlled unitary operations, including the powers, can be implemented at cost big O of n squared, we can count the total number of gates that we need. We have m Hadamard gates, and because m is linear in little n, the cost is big O of little n. We have n controlled unitary operations that each have cost big O of little n squared, so the total cost here is big O of little n cubed. And finally, the quantum Fourier transform has cost big O of little n squared. So the total cost is big O of little n cubed. In particular, we see that even with our modular exponentiation trick, the cost of the controlled unitary operations dominates. But in any case, it is a cost that's polynomial in little n. There are also some classical computations that are required, like computing the modular exponentiations and running the continued fraction algorithm. But those computations also have polynomial cost, and in fact, they can also be done in big O of little n cubed operations. So that is it. This is our efficient quantum algorithm for order finding problem, which we can use to factor integers efficiently, as I already mentioned earlier. There are certainly a lot of moving parts here. I went quickly and I swept a lot of details under the rug, but hopefully I've given you at least a basic idea for how this works. At the end of the day, what we have is Shor's algorithm for integer factorization. Shor didn't explain it in quite the same terms as this using phase estimation, but it is a standard way to describe Shor's algorithm. If you missed some of the details or you didn't quite catch how it works, that is okay. It definitely takes time to learn this stuff. And if it is the first time you're seeing it, you may find that going through it again is helpful. And that's the end of the lecture, in which we've covered the phase estimation problem, how we can solve it efficiently on a quantum computer, and how we can apply the solution to obtain Shor's algorithm for integer factorization. Thank you for your attention.